Hundreds of millions of years ago, Earth looked nothing like it does today. All the continents were joined together one vast land called Pangea. Imagine standing on a world where every ocean and mountain was connected. In this video, we'll travel back to that ancient time. If you enjoy this, please like, subscribe and share, and tell us in the comments, what do you think it would feel like to live on Pangea? Thank you for watching. Now let's begin. The planet is in motion even when it appears still. Beneath the crust, heat moves through the mantle in slow convection, currents shifting the surface in ways imperceptible to daily life. Continents slide, drift, and collide over spans of millions of years, shaping a surface that is always temporary. This motion is part of what geologists call the supercontinent cycle, a recurring rhythm in which the fragments of Earth's crust gather into a single massive landmass, remain unified for a time, and then break apart again. Each cycle takes hundreds of millions of years, and in that span the geography, climate and biology of the planet transform completely. The story of Pangea sits near the middle of this sequence, a stage where continents that had long wandered apart converged once more to form a world dominated by one great body of land surrounded by one vast ocean. The record of this event lies in the mountains, in the minerals of oceanic crust, and in the shifting magnetic grains that still point to directions long lost. In the late Carboniferous and early Permian periods, roughly 300 million years ago, the separate continents of an earlier Earth began closing in on one another. The crustal plates carrying what are now North America, Europe, and parts of Asia moved toward the southern landmass called Gondwana. Where they met, seas closed and mountains rose. Oceans such as the Reich and Iapetus were consumed as their floors were subducted into the mantle, leaving behind sutures marked by chains of folded rock. These collisions were not sudden. They unfolded at a rate of only a few centimeters per year, a pace slower than the growth of human fingernails, yet powerful enough to weld entire continents into a single entity over tens of millions of years. By the early Permian, almost all the planet's major landmasses had joined to form Pangea, a name later derived from Greek roots meaning all Earth. It was surrounded by a global ocean known as Panthalassa. The unification of land changed everything: the patterns of wind, the routes of ocean currents, the flow of life and evolution itself. When viewed on geological maps, Pangea appears as an enormous crescent, stretching from the southern polar region up toward the northern mid-latitudes, a configuration that altered the way the sun's energy moved across its surface. The equatorial regions received intense heat, while the vast interior far from any sea became dry and extreme in temperature. Rain rarely reached these central zones. Seasonal monsoons swept along the coasts driven by the differing heat between land and ocean, but the heart of the continent remained parched. The unity of the land also allowed life to spread widely. Forests of giant ferns, horsetails, and seed ferns covered the lowlands, while early reptiles roamed from what is now Africa to what is now Siberia. The connectedness of the terrain created migration routes that had never existed before, linking ecosystems across hemispheres. Yet the same vastness that allowed expansion also produced isolation within. Species adapted to narrow environments could find themselves stranded when rivers shifted or climates turned. Over millions of years, this dynamic balance between connection and separation would define evolution on Pangea. The existence of Pangea was first recognized not by direct observation, but by patterns seen in modern geography. In the early 20th century, Alfred Wegener noticed how the coastlines of South America and Africa seemed to fit together like puzzle pieces. He compared fossils, rock formations, and ancient glacial marks across continents, and proposed that they had once been joined. His idea of continental drift was initially met with skepticism, as no one could yet explain the mechanism that moved the continents. Later discoveries in plate tectonics provided that explanation, revealing the slow but constant movement of lithospheric plates over the mantle's convective currents. With this understanding, the reconstruction of Pangea became a precise science, supported by paleomagnetic data that showed how rocks recorded the direction of Earth's magnetic field at the time of their formation. As scientists traced these magnetic signatures across continents, they could map the paths of drift and rotation that brought the pieces together. What these reconstructions reveal is not just one moment of union, but an ongoing process. Before Pangea, other supercontinents had existed: Rodinia, which formed about 1 billion years ago, and perhaps Nuna before that. Each followed a similar pattern assembly through convergent stability across long ages and eventual fragmentation as heat and stress accumulated beneath the crust. The cycle reflects the deep engine of the planet itself. Mantle convection carries heat outward, and over immense spans of time it rearranges the continents in a slow dance between separation and reunion. The surface of Earth is thus both ancient and ever new, reshaped by forces that humans can barely measure within a lifetime. Pangea's formation marks one of the most complete examples of this process, and it serves as a reference point for understanding how global geography affects every other system. The joining of land altered the chemistry of the oceans by changing how sediments and nutrients were delivered to them. It influenced atmospheric composition by controlling volcanic outgassing and weathering rates. It even shaped the long-term evolution of climate, modulating the concentration of carbon dioxide in the air. These interactions made the early Permian world distinct from anything that came before or after. To imagine Earth during this time is to see a planet unified yet restless, a single landmass under wide skies bordered by an ocean so vast that its waves could travel around the world without meeting a shore. Across this immense landscape, the record of movement is still preserved. Folded mountain chains, rift valleys, and seams of ancient rock that tell of continents once torn apart and then drawn together again. The motions continue today, invisible on human timescales, but unstoppable in the deep rhythm of geological time. In this long view, Pangea is not an isolated event, but one phase in Earth's endless reshaping. A reminder that stability on this planet is only an illusion, and that even the ground beneath every mountain is in slow, ceaseless motion. A supercontinent is not simply a large landmass, but a configuration in which nearly all of Earth's continental crust comes together into one joined body. Pangea was the most recent example, but it was part of a longer sequence that may extend back over 3 billion years. Earlier versions such as Nuna and Rodinia came together and broke apart long before humans could imagine the scale of such cycles. Each one formed through the slow collisions of tectonic plates that float upon the mantle's viscous flow. When several major plates converge, mountain ranges rise and the crust thickens, drawing once separate continents into a single mass. This process takes tens to hundreds of millions of years, and its reversal through rifting and spreading takes just as long. Scientists describe this rhythm as the supercontinent cycle, a deep time heartbeat of the planet that reshapes oceans, climates, and ecosystems in recurring patterns. Pangea fits near the middle of this sequence, assembling after Rodinia's breakup, and before the projected creation of a future supercontinent, sometimes called Pangea Proxima. The conditions that led to Pangea's birth began during the late Paleozoic era, when continents such as Laurentia Baltica and Gondwana moved toward each other under the influence of converging plate boundaries. Subduction zones, regions where one plate descends beneath another, closed ancient oceans and drew the fragments together. As these collisions continued, the fragments welded into a continuous crustal mass surrounded by a single global ocean. The exact geometry of Pangea is now reconstructed through magnetic data and fossil distribution. It likely formed a giant crescent stretching from what is now Eastern Asia to the southern reaches of Antarctica, with a broad interior across present-day Africa and the Americas. The northern region, sometimes called Laurasia, consisted of the continents that would later become North America, Europe and Asia, while the southern region, Gondwana, included what are now South America, Africa, India, Australia and Antarctica. Between these two great halves lay a long zone of collision and mountain building. The joining of these regions created the world's most extensive continuous landmass, covering roughly 1/3 of the planet's surface and containing nearly all existing continental crust. Around it lay Panthalassa, the vast super-ocean that made up the rest of the globe. Such a planetary arrangement had profound consequences for every aspect of Earth's systems. With one large continent, ocean currents follow different paths than in a world of scattered islands and seas. Winds change direction according to the continent's immense size and topography. Climate patterns reorganize, creating zones of intense dryness at the interior and heavy rainfall along coasts. These global patterns shape not only weather, but also the evolution of life. Fossil evidence shows similar plant and animal species spread widely across what are now distant continents, their distributions reflecting the absence of barriers during the time of Pangea. This interconnected biosphere made the late Paleozoic one of the most biologically unified eras in Earth's history. Yet the forces that made Pangea were the same that would eventually tear it apart. Heat continued to build beneath the thickened crust as the mantle convected. Over millions of years, that heat weakened the lithosphere and began to form new rift zones, the first hints of the breakup that would follow in the Mesozoic era. But during its prime, Pangea represented the closest Earth has come to total continental unity. To understand what it meant for the planet, it helps to consider the scale of geological time. From the first movement of the plates that began to draw the fragments together, to the final welding that produced the complete supercontinent, more than 60 million years passed. That time span saw the emergence of forest, the spread of amphibians, and the rise of early reptiles capable of living away from water. The continents moved slowly, often less than 10 centimeters per year, yet those small motions added up to entire oceans closing. In the geological record, seams called sutures mark where one landmass joined another. These seams can still be traced today in mountain belts across several continents, revealing the pattern of Pangea's assembly. The Appalachians of North America align with the Caledonids of Europe, and the Anti-Atlas of Morocco, forming a single chain that once stretched thousands of kilometers across the joined continents. Farther east, the collision between Siberia and Kazakhstania created the Ural Mountains, another remnant of Pangea's central structure. Each of these ranges bears rocks that formed deep within ancient subduction zones or at the roots of vanished mountains. By studying these rocks, geologists can reconstruct the pressure, temperature and timing of the events that brought them together. Pangea's unification also left traces in magnetic minerals. When lava cooled at the surface, tiny grains of magnetite recorded the direction of Earth's magnetic field at that moment. By comparing the orientations preserved in rocks from different regions, scientists could determine how those regions moved over time. The matching signatures found across now separated continents confirmed that they were once connected. This understanding transformed geology in the 20th century, proving the reality of plate tectonics and continental drift. Beyond its physical formation, Pangea also represents a turning point in planetary climate. The closing of many ocean basins altered the exchange of heat and moisture between sea and land. vast continental interiors developed extreme temperature contrast between day and night, while the absence of polar seas changed how heat was distributed globally. The climate became more seasonal with strong monsoons near the coasts and long dry periods inland. These conditions influenced vegetation, promoting the spread of drought-tolerant plants and the evolution of animals capable of surviving in arid environments. The emergence of amniotic vertebrates that laid eggs on land coincided with these changes, suggesting that Pangea's environment helped drive one of the key evolutionary steps in Earth's history. The idea of a single supercontinent has also shaped the modern understanding of planetary habitability. It illustrates how the arrangement of land and sea can control not only climate, but also the stability of life's chemical cycles. When continents cluster, weathering rates change, volcanic gases are trapped or released differently, and the carbon cycle adjusts, influencing atmospheric composition. In this sense, Pangea was both a geological and a biological phenomenon, a temporary balance in which the crust atmosphere and biosphere interacted on a global scale. Eventually, this balance would shift again, but for tens of millions of years the planet experienced an era of unity, an Earth with one land and one ocean. The study of this ancient configuration continues to reveal how deeply interconnected the planet's systems are and how every continent, mountain and ocean is part of an unbroken story written across time. Surrounding the great landmass of Pangea stretched a single immeasurable body of water known as Panthalassa. This was the world ocean, covering nearly 70% of the planet's surface and wrapping around the continental expanse like a vast blue mantle. It was older than Pangea itself, born as earlier oceans merged when smaller continents collided. Panthalassa was deep-wide and largely uninterrupted, its waves travelling immense distances without meeting any barrier. Its sheer scale made it unlike any ocean known today. The circulation of its waters shaped the planet's climate, while its depths held ecosystems that adapted to conditions far removed from modern seas. In the absence of multiple land masses to deflect currents, Panthalassa likely featured a powerful equatorial current that circled the globe. Warm waters moved steadily from the tropics toward higher latitudes before cooling and descending into the deep. Near the poles, cold, dense water sank, completing a vast loop that redistributed heat and nutrients around the planet. These cycles, though invisible from the surface, were critical to the planet's balance. The stability of this ocean circulation influenced temperature gradients across Pangea and controlled how heat from the sun was stored and released. The strength and direction of these currents also depended on Earth's rotation, the tilt of its axis, and the arrangement of the landmass itself. Without narrow straits or enclosed seas, tides and waves in Panthalassa could travel uninterrupted for thousands of kilometers. The result was a calmer surface on a planetary scale, though storms along the continental margins could reach enormous power as they built energy across the open water. Along Pangea's coasts, where shallow shelves extended outward, nutrient-rich upwelling supported dense marine life. Fossil evidence from ancient sediments now found in Japan, Western North America and New Zealand suggests that coral reefs, sponges and ammonites thrived along these continental shelves. Farther offshore, the open ocean teemed with plankton and early forms of fish that left little trace except for fine-grained sediments laid down on the abyssal plains. These deep-sea deposits, preserved today in fragments of ancient oceanic crust, offer clues about the chemistry of Panthalassa's waters. Isotopic analyses of oxygen and carbon show that the ocean's temperature varied with the shifting climate on Pangea, cooling during glacial intervals and warming during periods of higher volcanic activity. The link between land and sea was intimate. When mountains rose through tectonic collision, Weathering released minerals that washed into the ocean, altering its composition. Volcanic eruptions emitted gases that reacted with seawater, changing its acidity and affecting the balance of carbon dioxide between ocean and atmosphere. Over millions of years, these exchanges formed a feedback system that regulated the global climate. The superocean thus acted as both mirror and moderator of the supercontinent's behavior. The name Panthalassa means all sea, and it is fitting. To imagine it is to picture an Earth dominated by water, with a single continuous horizon unbroken, except for the edge of Pangea. The colour of this ocean would have ranged from turquoise in the shallows to deep cobalt in the abyss. Light would have penetrated only the upper layers where photosynthetic plankton turned sunlight into energy. Below lay a dark and pressurized world where chemical reactions between seawater and volcanic rock supported microbial life around hydrothermal vents. These ecosystems, thriving on mineral energy rather than sunlight, may have resembled those that existed on the early Earth. Their presence in Panthalassa linked the planet's deep interior to its surface life, a connection that persists in the oceans of today. The dynamics of Panthalassa were also influenced by the gradual drift of Pangea across latitudes. As the supercontinent moved slightly northward during the Permian period, ocean circulation patterns adjusted. Monsoon winds strengthened along the coasts and upwelling intensified in certain regions. The exchange between atmosphere and ocean became more complex, affecting precipitation on land and the formation of desert belts across Pangea's interior. Sedimentary rocks that formed along the margins of Panthalassa now record these changing conditions through variations in grain size, mineral content, and fossil abundance. The preservation of marine sediments across multiple continents provides a detailed archive of ocean behavior through time. Within these rocks, tiny organisms called foraminifera encased in calcium carbonate shells serve as natural thermometers. The ratio of oxygen isotopes in their remains reflects the temperature of the water in which they lived. By analyzing these fossils, scientists have reconstructed ancient temperature gradients across Panthalassa, revealing that it maintained a stable equatorial warmth and cooler polar regions, similar in pattern, though not in intensity, to modern oceans. Yet stability in the deep time sense does not mean stillness. Panthalassa experienced its own cycles of change driven by tectonics, volcanism, and variations in Earth's orbit. Underwater mountain chains known as mid-ocean ridges spread new crust from the mantle, while subduction zones consumed old seafloor. Around the perimeter of the ocean arcs of volcanoes marked where the seafloor plunged beneath Pangea's edge. These zones, sometimes referred to as the Panthalassic Ring of Fire, mirrored the modern Pacific Rim in both activity and scale. They were regions of constant transformation, where magma-rose islands formed and sediments from the continent were drawn back into the mantle. Every part of the superocean was linked in a continuous cycle of creation and destruction. The circulation of Panthalassa also influenced atmospheric oxygen. As organic matter sank into the deep ocean and was buried, oxygen was released at the surface, allowing levels in the air to remain relatively high. During the late Carboniferous and early Permian, these levels supported the growth of enormous insects and amphibians on land. Thus, even the composition of the air depended on the quiet workings of the sea. The balance between marine burial and weathering on land formed a global chemical loop that stabilized the planet over immense spans of time. Panthalassa, though long vanished, remains central to understanding how Earth's systems operate. Its disappearance came as the supercontinent began to break apart and new oceans formed to replace it. Yet its legacy endures in the structure of today's Pacific, which may preserve remnants of its ancient crust deep below. The concept of a single world ocean is both a geological fact and a reminder of planetary unity. In the age of Pangea, the boundaries between ocean basins did not exist. Every current, every tide, and every storm belonged to one continuous body of water that surrounded all land and touched every shore. The record of that ocean endures in the rocks it left behind, in the chemistry of ancient sediments, and in the patterns of life that still trace their ancestry to a time when there was only one sea. Continents move not by their own will, but by the slow and persistent motion of Earth's interior. Beneath the crust, heat rises from the planet's core, setting the mantle into convection. In this cycle, hot material ascends toward the surface, cools and sinks again, dragging the lithospheric plates above it. Over immense spans of time, this movement shifts continents across the globe, opening and closing oceans, building mountains, and reshaping coastlines. The assembly of Pangea was one such consequence of this continual drift. It was not a single collision, but a sequence of convergences among many continental fragments, each moving at only a few centimeters per year, yet capable of transforming the face of the planet. During the late Carboniferous, roughly 320 million years ago, several large continental plates began to approach one another. To the north lay Laurussia, composed mainly of what are now North America and Europe. To the south lay Gondwana, a vast landmass containing South America, Africa, India, Australia, and Antarctica. Between them stretched the shrinking Reich Ocean, a body of water that had existed for more than 100 million years. Along its subduction zones, oceanic crusts sank beneath the advancing continental margins, carrying sediments and volcanic arcs toward collision. As these zones converged, fragments of island chains and smaller continental blocks were trapped and welded onto the edges of the larger plates. This process, known as accretion, thickened the crust and raised new mountain belts. By around 290 million years ago, the closure of the Rhisic Ocean was nearly complete. North America and Gondwana collided, fusing their crusts into the central spine of Pangea. At the same time, collisions elsewhere closed other oceans, such as the Paleotethys, linking the continents of Eurasia and bringing Siberia closer to the equatorial belt. Each of these movements left permanent marks in rock belts of metamorphic schist, granitic intrusions and folded strata that record the tremendous pressures of continental contact. The slow compression of the crust produced vast fault systems that extended for thousands of kilometers. The resulting mountain chains, some higher than today's Himalayas, formed along the seams where the continents met. The collision between North America and Africa, for instance, created the ancestral Appalachians, a chain that once stretched far beyond its current length and connected directly with mountains in what are now Scotland, Norway, and Morocco. To the east, the convergence of Siberia with Kazakhstania gave rise to the Ural Mountains, marking the boundary between what would become Europe and Asia. In each case, the process was the same. Subduction drew plates together. Compression thickened the crust and molten rock intruded into the deep roots of the growing ranges. Above these zones, earthquakes and volcanism were frequent, reshaping the landscape as new landforms rose and old ones eroded. As Pangea grew smaller, microcontinents such as Cimmeria drifted away from Gondwana and began their own journeys northward, preparing for later stages of collision that would further expand the supercontinent's outline. The formation of Pangea was therefore not a single event, but a long sequence of orogenies or mountain-building episodes occurring across several tens of millions of years. Each episode added new material to the continental crust and rearranged the pattern of seas and land. The interior of the newly formed continent became increasingly stable, while its margins remained active zones of compression and volcanism. The closing of the oceans did not happen quietly. Sediments that had accumulated for ages on the ocean floors were thrust upward, forming complex folds and nappies in the mountain belts. Marine fossils found high in the modern Appalachians and Alps are remnants of these ancient seas, their shells compressed into stone during the continental collisions. The joining of continents also affected the global carbon cycle. As mountains rose, their exposed rocks began to weather, drawing carbon dioxide from the atmosphere and cooling the climate. This cooling coincided with the expansion of polar ice during the late Carboniferous, a period when glaciers advanced across parts of Gondwana. Layers of tearlite rock formed from glacial debris still record this icy episode in regions such as South Africa, India, and Australia. The advance and retreat of these glaciers left striations and grooves on the bedrock aligned with the movement of ice sheets that once stretched thousands of kilometers across the southern hemisphere. The repeated freezing and thawing of these glacial cycles further altered sea levels, exposing and flooding coastal plains in rhythmic succession. The assembly of Pangea thus produced both immense mountains and deep climatic shifts. The rearrangement of continents also redirected ocean currents and atmospheric circulation. As the continental masses came together, equatorial currents were deflected, and the exchange of heat between low and high latitudes changed. The newly closed seas no longer moderated temperature extremes, and the interior of Pangea began to dry. Deserts spread across its center, while coastal regions remained humid and monsoonal. These environmental contrasts left distinct signatures in sedimentary rocks. Red sandstones and evaporite deposits formed from the evaporation of inland seas became widespread across the interior basins. In contrast, coal-bearing strata accumulated along the humid margins, particularly in what are now North America and Europe, where lush swamp forests thrived before being buried and compressed into seams of carbon. This pattern of deposits provides a geological map of ancient climates, revealing how the assembly of continents directly shaped the environment. The collisions that built Pangea were relentless, yet orderly, following the slow rhythm of tectonics. Each continent approached another as if drawn by gravity, though the true cause lay deeper in the convection of the mantle and the density of the sinking oceanic crust. Where plates met, immense pressures accumulated until the crust fractured or bent. In some regions, subduction continued for millions of years after collision, producing belts of granite and volcanic rock that extended across entire mountain systems. In others, the crust thickened so much that it began to collapse under its own weight, spreading laterally and forming high plateaus. These variations made the surface of Pangea a mosaic of elevated mountains and broad lowlands. The mountain belts became sources of sediments that rivers carried outward into vast deltas and inland seas. Over time, erosion reduced the peaks, but the roots of those mountains still lie deep beneath the surface today. Their presence reveals the immense forces that once compressed the planet's crust into a single mass. The unification of the continents during this time represents one of the most dramatic reorganizations in Earth's geological history. It was an era of construction on a planetary scale when continents long separated by oceans met again in slow embrace, closing the chapter of wandering that had begun hundreds of millions of years earlier. The scars of those collisions remain as silent witnesses in the rocks each layer, and fold a record of motion so vast that it can only be measured in the language of deep time. As the continents locked together to form Pangea, pressure along their margins forced the crust upward, building mountain chains of extraordinary size and complexity. These mountains were not isolated peaks, but immense systems stretching for thousands of kilometers, the physical seams of the supercontinent's creation. Their origins lie in the immense compressive forces generated where plates collided, folding, faulting, and stacking layers of rock upon one another until they rose to monumental heights. Among the most notable of these were the Appalachians in what is now North America, the Variscan Belt across Europe, and the Ural Mountains dividing modern Russia. Each was part of a single connected orogenic system that once curved across the heart of Pangea, linking what are now distant lands into a continuous ridge. The Appalachians began forming when Laurentia collided with the microcontinent Avalonia and then with the northern edge of Gondwana. These successive collisions compressed marine sediments and volcanic arcs that had accumulated along the margins of the ancient Iapetus and Rheic oceans. As the crust crumpled, metamorphic rocks formed deep underground, and magma intruded upward as granite bodies. The mountain belt that emerged was vast, rising as high as the present-day Himalayas. Erosion later softened its profile, but deep within its roots remain rocks that record the incredible pressures of its formation. Across the Atlantic, the Variscan Belt told the same story. It stretched from present-day Spain through France, Germany, and into Poland, created by the collision of Gondwana with Laurussia. These mountains once joined seamlessly with the Appalachians before the Atlantic Ocean opened much later, dividing their remnants. To the east, another major collision brought together Siberia and Kazakhstania, closing the Uralian Ocean and forming the Ural Mountains. Their rocks preserve a detailed record of subduction volcanic activity and accretionary wedges where oceanic crust was thrust upward. The Urals stand today as one of the few ancient origins still visible above sea level, an enduring remnant of Pangea's central spine. Along the southern margins of Gondwana, yet another great orogenic system arose, the Gondwanid Belt. Extending across what are now South Africa, Antarctica, Australia, and South America, it formed when subduction zones consumed oceanic crust along the edge of the southern supercontinent. Volcanic arcs and folded sediments testify to this prolonged convergence, linking the southern continents in a continuous chain. These mountain systems reshaped global geography. They altered wind patterns, redirected rivers, and influenced rainfall across vast regions. The rising ranges trapped moisture on one side, creating rain shadows and expanding arid zones on the other. The uplift also exposed fresh rock to weathering, which drew carbon dioxide from the atmosphere and contributed to global cooling during the late Carboniferous. Glacial deposits found in India, South Africa, and Australia mark this time, showing how mountain building and climate were intertwined. The mountain belts of Pangea did more than change the surface, they restructured the deep interior of the crust. As compression thickened the continental lithosphere, the lower layers became hot and ductile. Over time, the dense lower crust began to flow laterally, redistributing mass and stabilizing the growing ranges. In some regions, this process created broad plateaus, while in others, it produced localized zones of subsidence where sediment accumulated. The balance between uplift and erosion maintained a dynamic equilibrium for millions of years. Rivers originating in the highlands carried immense quantities of material toward the surrounding basins. These sediments built deltas and coastal plains that would later become important geological archives. In the interior of Pangea, the erosion of the mountain belts filled vast depressions with red sandstones, mudstones, and evaporites. These deposits recorded the arid conditions of the continental interior and preserved traces of life that adapted to them. The sheer scale of mountain building during Pangea's formation affected the planet's atmosphere and ocean systems. As uplift increased the elevation of continental interiors, global wind patterns shifted. Air masses cooled as they crossed the high terrain, and rainfall became concentrated along mountain fronts. The resulting rivers formed enormous drainage networks that carved deep valleys and transported sediments thousands of kilometers across the continent, The long-term drawdown of carbon dioxide caused by weathering also influenced the chemistry of the oceans, promoting the deposition of carbonate minerals and helping stabilize global climate. These processes linked tectonics, erosion, and climate into a single interconnected system that defined the late Paleozoic world. In addition to their geological impact, the mountains of Pangea were cradles of biological change. The newly formed uplands created varied environments, humid valleys, high plateaus, and arid foothills that encouraged the diversification of terrestrial life. Plants evolved deeper root systems to anchor themselves in rocky soils, and early reptiles adapted to the fluctuating climates of the upland regions. Fossil evidence from coal measures and red beds indicates that lush forests grew in low-lying basins near the mountains, while more drought-tolerant vegetation covered the higher slopes. These ecosystems contributed to the vast coal deposits that characterize the Carboniferous and Permian periods, storing the organic carbon that had once circulated through the atmosphere. The Appalachians, Variscans, and Urals together mark the complete suturing of the continents into one. Their alignment across thousands of kilometers shows how deeply the planet's crust was reorganized during this time. Seismic studies of their modern remnants reveal thick roots, extending far into the mantle remnants of the dense lithospheric keels that supported the ancient ranges. Over time, erosion stripped away the upper layers, but the buried cores remained stable cratons, rigid regions of the crust that now form the foundations of the continents. Even after hundreds of millions of years, these deep structures continue to influence modern geography. River systems, coastlines, and even patterns of resource distribution reflect the architecture established during Pangea's assembly. The mountains also left a legacy of mineral wealth. As magmas cooled and hydrothermal fluids circulated through fractures, they concentrated metals such as copper, gold, and tin. Many of the world's great ore deposits trace their origins to the tectonic events of this era. Thus, the economic geography of the modern world still bears the imprint of forces that acted during the time of Pangea. From a global perspective, the formation of these mountains completed the process of continental convergence. With nearly all land joined together, Earth entered a phase of relative stability, at least on the surface. The supercontinent would endure for more than 100 million years before the same internal forces that created it began to tear it apart. Yet during its long existence, the highlands of Pangea shaped not only the flow of water and air, but also the evolution of life and the balance of the planet's atmosphere. They were both the scars and the engines of a world in transition, a testament to the deep, slow power of tectonics. The remains of those ancient ranges, though, eroded and far apart today, still whisper the story of a time when mountains once connected continents into one continuous arc of stone beneath a single sky. When the continents fused into one immense body, the planet's climate entered a new and complex state. The geography of Pangea determined how sunlight, air, and water interacted on a global scale, producing contrasts far greater than those seen on modern Earth. The supercontinent's sheer size created regions so distant from the ocean that moisture rarely reached them, while coastal zones endured strong monsoons, driven by the annual cycle of heating and cooling. This arrangement shaped the late Paleozoic and early Mesozoic worlds into a mosaic of environments ranging from polar glaciers to vast deserts. Climate in this era cannot be described by a single pattern. It was an intricate system of extremes bound together by the slow rhythms of Earth's orbit and the constant exchange of heat between land and sea. At the heart of Pangea, the continental interior lay thousands of kilometers from the nearest coastline. Without nearby oceans to moderate temperature, these inland regions experienced wide daily and seasonal variations. Summers were intensely hot while winters turned cold and dry. The soil was thin, vegetation sparse, and the wind carried fine dust across plains that stretched unbroken for hundreds of kilometers. These arid zones are now recorded in the rock record by layers of red sandstone and evaporate minerals such as halite and gypsum, remnants of salt lakes that formed when shallow waters repeatedly evaporated. In contrast, the coastal regions were humid and dynamic. During the summer, when the interior heated faster than the surrounding ocean, moist air flowed inland, generating strong monsoon rains. These seasonal downpours fed great river systems that carved valleys and built fertile floodplains. During the winter, the process reversed. Cooler land pushed air seaward, bringing dry winds and cooler temperatures to the coasts. Such alternating wet and dry seasons shaped the vegetation favoring plants, with adaptations to fluctuating water availability. In these zones, forests of giant horsetails, seed ferns, and conifers grew densely, forming the coal swamps that would later harden into thick seams of carbon. Farther south, Gondwana experienced another kind of climate entirely. The southern part of the supercontinent lay over the South Pole, where ice sheets spread during cooler phases of the late Carboniferous. Glacial deposits found in South Africa, India, and Australia mark the extent of these frozen landscapes. Striations carved into bedrock show the direction of ice movement, while layers of tillite record the grinding debris of retreating glaciers. As the planet warmed during the Permian, these ice sheets melted, flooding lowlands and altering sea levels around the world. The alternation of glacial and interglacial periods left a rhythmic pattern in the sedimentary record known as cyclothems. Repeated sequences of coal shale, limestone, and sandstone that reflect changing water levels and climates. The unity of the continents also altered the circulation of the atmosphere itself. With a single landmass stretching across much of the equator, large-scale wind belts formed with little interruption. Trade winds blew steadily from east to west in tropical regions, while westerlies dominated the higher latitudes. The vast surface area of land increased the planet's ability to absorb solar radiation during the day and release it at night, amplifying temperature contrast between regions. This imbalance drove powerful atmospheric cells that carried moisture across thousands of kilometers, only to drop it near the coasts or mountains and leave the interior dry. Dust from the central desert spread across the supercontinent, sometimes reaching the coastal seas where it fertilized marine ecosystems with iron and other nutrients. The interaction between atmosphere and land also influenced the chemistry of the air. During the Carboniferous, before Pangea reached full-size, oxygen levels were unusually high, possibly over 30%, due to the burial of vast amounts of plant material in swamps. This abundance supported the growth of large insects and amphibians. As Pangea matured and climates became drier, vegetation declined and oxygen levels gradually fell. At the same time, volcanic activity associated with ongoing tectonics released carbon dioxide, helping to warm the planet after the long glacial episodes. The balance between these gases shaped the transition from the cooler Carboniferous to the warmer Permian world. The ocean played a vital role in this climatic system. The single global ocean Panthalassa acted as a massive reservoir of heat and moisture. Warm equatorial waters circulated poleward, while cold polar currents sank and returned toward the tropics in the deep ocean. This global conveyor regulated temperature, but could not fully offset the extremes produced by the continent's size. Along the margins of Pangea, the interaction between oceanic and continental climates produced unique weather patterns. Fossilized dune fields in regions such as modern North America and Namibia show evidence of strong prevailing winds, their orientations revealing the direction of ancient atmospheric circulation. The shapes of these dunes preserved in cross-bedded sandstone record the dominance of arid conditions across much of the supercontinent's core. Climate also changed with time. During the Permian period, volcanic activity increased along Pangea's margins, releasing carbon dioxide and creating a gradual warming trend. In the later part of the Permian, this warming intensified, drying the interiors even further and leading to the collapse of many swamp ecosystems. The result was the end of the extensive coal-forming environments of the Carboniferous. The Permian climate became harsher and less hospitable, setting the stage for one of the largest mass extinctions in Earth's history at the boundary with the Triassic. This event, though caused by multiple factors, was closely tied to the volatile climate of a unified world. The supercontinent's configuration magnified feedback loops. Dry land reflected more sunlight, reducing cloud cover, while reduced vegetation allowed more dust and carbon dioxide to circulate. These shifts transformed not only temperature and rainfall, but also the chemistry of the oceans, altering their capacity to support life. Yet even amid these extremes, certain regions of Pangea remained stable and fertile. Along the equatorial zones, rivers and wetlands supported diverse ecosystems. Fossil plants such as Glossopteris and chordates indicate broad climatic gradients, while reptile and amphibian fossils reveal adaptation to both humid and arid habitats. Seasonal climate forced evolution to favor resilience, driving the spread of species capable of surviving drought and fluctuating temperatures. From a geological perspective, the climate of Pangea demonstrates the deep connection between continental arrangement and atmospheric behavior. Modern computer models confirm what the rocks suggest when continents cluster their interiors dry and their edges become storm-prone. The concentration of landmass at low latitudes enhances monsoons but limits the flow of moisture inland. The pattern repeats through Earth's history whenever supercontinents form. In this way, Pangea provides a template for understanding not only the past, but also the long-term future of climate on a tectonically active planet. It reveals that geography and atmosphere are inseparable, each shaping the other across the slow pulse of geological time. The circulation of air and water around Pangea was a global system unlike any before or since, a planetary mechanism driven by the interaction between the immense landmass and the surrounding superocean Panthalassa. With nearly all continents joined the planet's rotation, an axial tilt sculpted winds and currents into sweeping continuous patterns that govern temperature, rainfall, and even the distribution of life. These patterns did not remain fixed but evolved as Pangea shifted slowly northward, changing the alignment of ocean basins and altering the shape of coastlines. The forces that connected air, sea and land were part of a single network of motion that linked every region of the world. At the equator, intense solar heating caused warm air to rise, producing a band of low pressure that encircled the planet. This rising air released moisture in torrential rains along the coastal zones, creating fertile belts near the edges of Pangea. As the air moved poleward, it cooled, descended and turned back toward the equator, forming massive convection cells. These cells, combined with the planet's rotation, produced prevailing trade winds that blew steadily from east to west across the tropics. In higher latitudes, westerly winds moved in the opposite direction, driving storms along the mid-latitude coasts. Over Panthalassa, these winds generated powerful currents that circled the globe, their momentum uninterrupted by continental barriers. The main equatorial current flowed westward, while return flows at mid-latitudes carried cooler water eastward, completing vast gyres that transferred heat between the equator and the poles. This oceanic circulation moderated global climate, but it also shaped local environments in ways that depended on geography. Where warm surface water met cooler currents upwelling, brought nutrients from the deep sea, sustaining rich marine ecosystems. These upwelling zones likely formed along the western coasts of Pangea's continental margins, similar to those seen today off Peru or Namibia. Fossilized marine sediments from regions now forming part of North America and Japan preserve evidence of high biological productivity during these intervals marked by layers rich in organic carbon and microscopic plankton remains. The monsoon system, driven by temperature contrasts between land and sea, added another layer of complexity. During the summer months of each hemisphere, the continental interior heated rapidly under the sun, causing air to rise and drawing moist winds from the ocean. When these winds reached the land, they released heavy rainfall near the coasts and along mountain slopes. In winter, as the land cooled, high-pressure systems formed over the interior, reversing the flow and sending dry winds outward. This cycle, magnified by the size of the supercontinent, produced some of the most intense monsoons in Earth's history. Seasonal flooding shaped the sedimentary record of the time, leaving alternating layers of silt and sand that trace the rhythmic advance and retreat of rivers swollen by the rains. The strength of these monsoons also controlled the spread of vegetation. In the wet season, dense forests and swampy lowlands expanded along the coasts, while in the dry season the interior remained barren, its soil baked and cracked. The feedback between vegetation and atmosphere was significant. Forests added moisture through transpiration, while bare land increased heat reflection, further strengthening temperature contrasts. The balance between these processes fluctuated as the planet moved through orbital cycles that changed the amount of sunlight reaching different latitudes. Periods of greater monsoon intensity corresponded with warmer global temperatures, while weaker cycles led to extended droughts. The pattern of rainfall dictated where rivers formed and how sediments were distributed. Major river systems such as the ancestral Mississippi-Niger and Indus analogues flowed across the vast plains joining inland seas or evaporating in arid basins. Each carried eroded material from the mountain belts into the lowlands, where it settled in thick layers that now preserve records of ancient weather and hydrology. Some of these rivers were seasonal active only during monsoon months, while others carved permanent channels through resistant rock. The shifting paths of these waterways reveal the dynamic nature of the supercontinent's climate. Ocean currents did more than move water. They transported energy across hemispheres. Warm currents flowing northward from equatorial Panthalassa prevented extreme cooling at higher latitudes, while cold currents sinking toward the equator tempered tropical heat. The interaction between these currents created regions of turbulence, where temperature differences were most pronounced. These zones of mixing were crucial for marine life, distributing oxygen and nutrients throughout the water column. Geological evidence from black shales deposited in Panthalassa indicates that at times deep waters became depleted of oxygen, likely during warmer intervals when circulation slowed. These anoxic events preserved organic material that would later form source rocks for hydrocarbons, a reminder of how ocean circulation leaves lasting chemical fingerprints in stone. The polar regions of Pangea were equally dynamic. During the Carboniferous parts of Gondwana lay over the South Pole covered by ice sheets. As the continent drifted northward in the Permian glaciation waned and the poles became warmer, but the contrast between high and low latitudes remained strong. Atmospheric circulation carried cold air from the poles toward the equator, reinforcing the desert conditions of the continental interior. In this way, global circulation linked the fate of distant regions. Snow accumulation in the south could influence rainfall near the equator thousands of kilometers away. The gradual northward drift of Pangea also affected the distribution of ocean basins and the orientation of currents. As the supercontinent moved, Panthalassa expanded in some directions and contracted in others, redirecting flow paths. Meanwhile, the opening of the Tethys Ocean along Pangea's eastern margin introduced a new route for warm waters between the equator and the mid-latitudes. This secondary ocean, though smaller, began to modify global circulation patterns by creating new pathways for heat exchange. The climate became more differentiated, with wetter conditions developing in certain tropical zones and greater aridity in the interior. These changes were slow but cumulative, unfolding over millions of years. They demonstrate how the position of continents determines the movement of air and sea, and how small shifts in geography can propagate through the entire planetary system. The atmosphere, the ocean, and the land operated together as a coupled engine. When mountain ranges altered the flow of winds, ocean currents adjusted. When rainfall patterns changed, erosion rates, sediment delivery to the ocean shifted, influencing marine chemistry. Every component responded to the others in a continuous feedback cycle. In the deep time view, Pangea's climate and circulation represent an experiment conducted by nature on the grandest scale, a test of what happens when nearly all land is joined and surrounded by one boundless sea. The outcome was both balance and instability, stable in the sense of recurring seasonal rhythms, unstable in the long-term trends that oscillated between ice and heat, humidity and drought. Through these cycles, Earth systems evolved together, leaving behind a record etched into rocks, fossils and isotopes that continue to reveal how profoundly the shape of the planet governs the flow of its air and water. Life during the age of Pangea existed on a connected world where plants and animals could spread across immense distances unimpeded by wide oceans. This unity allowed species to migrate from one region to another, creating ecosystems that stretched from the equator to the polar edges of the supercontinent. Yet the same vastness that encouraged expansion also imposed limits. Climate extremes divided the land into humid belts, temperate forests, and immense dry interiors, and only those species able to adapt to shifting conditions endured. The late Carboniferous and Permian periods witnessed an evolutionary landscape in flux, where the union of continents reshaped the pathways of survival. The coal swamps that had flourished earlier in the Carboniferous began to recede as the global climate dried. These lush wetlands, filled with giant lycopsids, horsetails, and seed ferns, had once formed dense forests stretching across the equatorial regions of Laurussia and Gondwana. Their decomposition had enriched the atmosphere with oxygen and produced the coal seams that still fuel human civilization today. As aridity increased, these humid forests retreated toward coastal plains, and river valleys replaced inland by gymnosperms plants with seeds encased in cones or hard coverings. Conifers, cycads, and ginkgophytes became dominant, better suited to withstand drought and temperature variation. These new plants formed open woodlands and scrublands where ferns still survived in shaded hollows. The changing vegetation altered the balance of life on land. Herbivorous insects diversified to feed on the tough resinous leaves of conifers, developing stronger mouthparts and new life cycles. The decline of swamp vegetation reduced habitats for amphibians, which had relied on moist environments to reproduce. In their place, reptiles began to dominate. The evolution of the amniotic egg, a structure with a protective shell that prevented desiccation, freed reptiles from dependence on water, allowing them to colonize the dry interiors of Pangea. Early reptiles such as the synapsids and diapsids spread widely, giving rise to a variety of forms that filled ecological roles similar to those of mammals and reptiles today. Synapsids, sometimes called mammal-like reptiles, developed differentiated teeth and more efficient metabolisms, enabling them to regulate body temperature and thrive in cooler conditions. Among them were large herbivores like Edaphosaurus and predatory species such as Dimetrodon, recognized by its tall sail-like fin that may have helped regulate heat. Their fossils are found across North America, Europe, and South Africa, evidence of the open migration routes across Pangea. In the oceans of Panthalassa, life followed its own patterns. Marine communities adjusted to new currents, salinity and temperature regimes created by the vast and unified ocean. Coral reefs expanded along the continental margins, built by sponges, bryozoans, and calcareous algae. Cephalopods such as ammonites and nautiloids swam through warm, shallow seas, while fish evolved new forms in response to predators and changing habitats. In the deeper waters, trilobites, which had dominated marine ecosystems for hundreds of millions of years, declined toward extinction, replaced by new arthropods and early crustaceans. The stability of the ocean's chemistry supported a diverse array of invertebrates, but fluctuations in oxygen levels during the late Permian disrupted these ecosystems. Episodes of ocean stagnation when circulation slowed and deep waters became depleted of oxygen led to localized die-offs that foreshadowed the greater crises to come. On land, the unification of habitats encouraged the spread of fauna between regions. The fossil record reveals similar assemblages across continents now separated by thousands of kilometers. The plant Glossopteris, for example, once covered vast portions of Gondwana, and its remains are found in South America, Africa, India, Australia, and Antarctica. This shared distribution later helped confirm the reality of continental drift. In northern regions, the widespread occurrence of the reptile Mesosaurus in both Africa and South America provided further proof of ancient connection. These creatures lived in freshwater environments, and their fossils now lie on opposite sides of the Atlantic testimony to the time when no such ocean divided them. Ecosystems on Pangea reflected gradients of latitude and elevation more than geographic barriers. In equatorial zones, swampy lowlands supported dense forests and diverse insect life, including dragonflies with wingspans longer than a human arm. At mid-latitudes, open woodlands gave way to grassless plains where reptiles grazed and hunted. Farther toward the poles, cool climates fostered hardy vegetation and seasonal ice. This latitudinal zonation mirrors modern patterns, but on a far grander scale amplified by the supercontinent's size. The continuity of land also influenced evolution through competition and replacement. Species that once evolved in isolation met as their habitats merged. Some groups expanded, others disappeared. Amphibians declined in diversity, unable to compete with reptiles better suited to dry environments. Meanwhile, insects radiated into new forms, becoming pollinators, scavengers, and decomposers. The intricate web of interaction among these organisms shaped the ecosystems of the Permian world, creating networks of dependency that balanced energy and matter across entire continental scales. In the wetlands that persisted, new reproductive strategies emerged. Seed ferns developed windborne pollen, reducing their reliance on water. Early gymnosperms produced cones designed to protect seeds from desiccation and fire. These adaptations mirrored the broader trend toward resilience in an increasingly harsh climate. Fire itself became a regular part of the landscape, fueled by the dry vegetation and high oxygen levels. Charcoal layers in Permian rocks show that wildfires burned across the continents, clearing old growth and stimulating regeneration. Such cycles of destruction and renewal formed part of Pangea's ecological rhythm. The interplay between life and environment reached a delicate balance. Plants drew carbon dioxide from the air, cooling the planet, while volcanic eruptions replenished it, maintaining warmth. The erosion of newly raised mountains delivered nutrients to coastal seas, supporting marine productivity that fed fish ammonites and planktonic organisms. The burial of organic matter in sediments locked away carbon, slowly influencing the global climate. In every ecosystem, from arid desert to deep ocean trench, these exchanges formed a chain that linked the biosphere with the geosphere and atmosphere. Yet beneath this dynamic equilibrium lay instability. Toward the end of the Permian, volcanism intensified in what is now Siberia, releasing immense amounts of gas that would soon tip the balance of climate and life. Before that cataclysm, however, the biosphere of Pangea flourished in diversity and adaptation. It was a world both familiar and alien, an Earth where giant insects filled the skies, reptiles ruled the plains, and conifer forests stretched from coast to coast beneath a single sun. The unity of the continents had created a stage upon which evolution could act globally, connecting every ecosystem in a continuous web of life that reached from the smallest fern spore to the largest predator. Its traces endure in fossils scattered across today's separated continents, silent witnesses to a time when the entire planet's living fabric was woven together across one boundless land. Across the expanse of Pangea, rivers became the veins of the supercontinent, carving through mountains, crossing deserts, and carrying the eroded remnants of highlands toward distant seas. These waterways were far larger than any single drainage system today, some extending for thousands of kilometers before reaching deltas at the edge of Panthalassa. Their slow, persistent movement shaped the surface of the land and preserved its history in layers of sediment. Each river carried a record of its surroundings, minerals from mountains, pollen from forests, and the remains of plants and animals swept away by floods. Over millions of years, these materials accumulated in basins where time compressed them into stone. Through these deposits, scientists reconstruct the geography and climate of Pangea, reading the story of its rivers as if they were lines in an ancient chronicle written in sand and mud. The river systems of the supercontinent were complex and dynamic. Some drained the high mountain belts that had formed during the continental collisions, while others meandered across the flat interiors flowing into shallow inland seas. In the humid equatorial regions, rivers ran year-round, swollen by monsoon rains that fell predictably each season. Their floodplains were broad-lined with dense vegetation and prone to cycles of inundation and retreat that created rich soils. In contrast, in the arid interior basins, rivers were intermittent, flowing only after rare storms. These ephemeral channels, known as wadis, left behind braided networks of sand and gravel that later turned to sandstone. The alternation between wet and dry periods built rhythmic sedimentary layers, fine silts deposited during calm intervals and coarser material laid down in floods. These repeating patterns, preserved as cross-bedded strata, now reveal the pulse of climate across deep time. In regions where mountain belts bordered lowlands, rivers formed massive alluvial fans spreading sediments outward in broad cones. Each flood carried material from the highlands, slowly wearing down peaks and filling adjacent basins. The balance between uplift and erosion determined how landscapes evolved. When mountains rose faster than they eroded, steep valleys formed. When erosion prevailed, the land flattened into plateaus. Over millions of years, this interplay sculpted Pangea's surface into a mosaic of plains, ridges, and basins, all connected by networks of water. The sediment transported by these rivers ultimately reached deltas and shallow seas, where it settled and compacted into new rock. These deltic deposits are among the most detailed archives of Pangea's environmental history. Layers of mudstone and shale preserve delicate fossils of plants and animals that live near the water's edge, ferns, conifers, insects, and amphibians. Each layer represents a brief moment of stability before the next flood buried it. In some places, entire forests were entombed in silt, their trunks still standing upright within the rock, silent witnesses to ancient storms. Such deposits are found across North America, Europe, and Asia, their similarities demonstrating that Pangea's river systems shared comparable dynamics across continents. The sediments carried by rivers did not only build landscapes, they also shaped the chemistry of the ocean. As weathering broke down minerals on land, elements like calcium iron and silica washed into Panthalassa. These nutrients supported marine life and influenced the deposition of limestone and chert on the seafloor. In this way, the rivers connected the continental interior to the global carbon and nutrient cycles. They acted as conduits between mountain and sea, transferring material from the peaks of Pangea to the abyssal plains of the superocean. Over time, thick accumulations of sediment buried organic matter, locking carbon beneath the surface and helping to regulate the planet's atmosphere. The hydrological systems of Pangea also mirrored the planet's seasonal rhythm. In the equatorial zones, strong monsoons fed immense deltas comparable to those of the modern Ganges or Amazon. Farther inland, seasonal streams filled ephemeral lakes that evaporated under the sun, leaving behind salt flats and gypsum deposits. These evaporite layers found in present-day North Africa, the Middle East, and western North America reveal that much of Pangea's interior lay under extreme aridity. Yet even in these harsh environments, life persisted. Fossilized footprints of reptiles, amphibians, and early mammals mark the ancient riverbanks, showing where creatures came to drink or hunt. In some places, trackways stretch for hundreds of meters across former mudflats, their patterns preserved by the baking heat of the sun, and later entombed by shifting sands. The rivers also recorded episodes of climatic change. During cooler intervals, glaciers in the southern highlands advanced grinding mountains into fine rock flour that was carried northward by meltwater. When these glacial streams reached warmer latitudes, they deposited layers of silt, rich in distinctive minerals, allowing scientists to trace the movement of ancient ice across continents. As the climate warmed again in the Permian, these sediments gave way to coarser river deposits, marking the retreat of ice and the expansion of arid landscapes. In this way, the stratigraphic record of rivers and deltas forms a continuous record of global transitions from cold to warm, from wet to dry. The sedimentary basins of Pangea later became repositories of geological resources. The burial of organic matter in ancient river deltas produced coal oil and natural gas, the compressed remnants of forests and plankton that thrived under the supercontinent's variable climate. Iron and other metals concentrated in the sediments of oxidized floodplains, forming deposits that would be mined hundreds of millions of years later. Thus, the processes that shaped Pangea's rivers also laid the foundations for much of Earth's future economic geology. The delta systems of the time were among the most productive environments on Earth. In shallow estuaries, tidal currents mixed fresh water with the salt of Panthalassa, creating gradients of salinity that fostered abundant life. Mollusks, fish, and amphibians occupied these zones, feeding on detritus carried from inland forests. The remains of these organisms accumulated in fine sediments, leaving behind fossil assemblages that bridge land and sea. These transitional environments demonstrate how intimately connected terrestrial and marine systems were on a planet unified by one landmass and one ocean. Even as tectonic forces and climate shaped the large-scale structure of Pangea rivers, continuously reworked its surface, redistributing sediments and renewing landscapes. Their constancy amid geological upheaval offers a reminder of how water persists as a stabilizing force across Earth's history. It erodes transports and deposits, carving the planet's memory into layers of stone. On Pangea, that memory was global, flowing unbroken across thousands of kilometers, recording not only the geography of a world that no longer exists, but also the rhythm of life and change that continues today. In every outcrop of sandstone, every ripple mark preserved in ancient rock, the trace of these rivers endures a testament to the quiet persistence of water, shaping a continent that once encompassed all the earth. At the heart of Pangea stretched vast regions where rain seldom fell, and where the land baked under relentless sunlight. These were the great interior desert zones, so far from any ocean that moisture could not cross the distance. Surrounded by mountain chains and shielded from maritime winds, the air above these plains shimmered with heat during the day and cooled sharply at night. For millions of years, these deserts covered what are now parts of North America, North Africa, and Asia, leaving behind immense deposits of red sandstone, siltstones, and evaporite minerals that tell of an environment of extremes. The rock layers reveal a world of wide basins filled with dunes, dry riverbeds and salt pans, an arid expanse stretching across the center of the supercontinent like a scar of desolation. The formation of these deserts was a direct consequence of Pangea's size and shape. With landmass extending from pole to pole, air currents that once carried oceanic moisture were disrupted. Warm air rising near the equator descended again in the subtropics, as dry high-pressure systems suppressing rainfall. These descending air masses created belts of aridity across the interior, much like the deserts that now ring the subtropical latitudes, but far larger and more continuous. The absence of vegetation allowed the wind to sculpt the land freely. Dunes formed in crescent shapes, their crests migrating slowly over the years, while sandstorms swept fine grains across the basins, building layers that today reach hundreds of meters in thickness. The iron-rich minerals within the sand oxidized under the dry conditions, staining the sediments in shades of red and orange that remain visible in modern outcrops across regions such as the southwestern United States, Morocco, and Central Europe. These colors, known as desert varnish, are one of the hallmarks of ancient arid climates. Within these immense deserts, occasional rains brought sudden but brief transformations. Flash floods carved channels through the sand, depositing coarser sediments in winding fans that spread outward from the mountains. As the water evaporated, it left behind crusts of salt and gypsum. These evaporite layers alternate with sandstones in rhythmic succession, marking the seasonal and climatic variations that define the environment. In some basins, the concentration of salts reached such levels that entire beds of halite or rock salt formed. Over time, these deposits became buried and compressed, their presence today providing evidence of prolonged evaporation in the heart of the supercontinent. Life in these regions was sparse but not absent. Fossil footprints preserved in fine-grained mudstones show that reptiles and small amphibians crossed the dunes, perhaps in search of temporary pools after rainfall. Their tracks weave across the surfaces of ancient dunes and streambeds, frozen in mid-stride by the drying mud and later buried by shifting sands. Plant fossils are rare but include hardy conifers and seed ferns adapted to drought their roots, penetrating deep to reach groundwater. These pioneer plants stabilized dunes and formed small oases along intermittent streams. Their remains, though fragmentary, reveal the resilience of life under conditions that tested every form of adaptation. The atmosphere over the deserts of Pangea would have been filled with dust carried high into the sky by constant winds. These fine particles drifted across the continent, settling eventually in distant lakes or along coastal plains where they enriched the soil with minerals. Dust from the interior deserts likely influenced climate far beyond their boundaries, reflecting sunlight and affecting patterns of rainfall along the continental margins. Even the chemistry of Panthalassa may have been touched by this process, as iron-bearing dust blown over the ocean fertilized plankton growth in surface waters. Thus, the lifeless heart of Pangea still played a role in sustaining life at its edges, linking barren land to fertile sea in an invisible cycle. Geological formations that record these ancient deserts are widespread today. In North America, the red sandstones of the Permian and Triassic, such as those exposed in the southwestern states, reveal ancient dune fields now frozen in stone. In Europe and North Africa, similar strata known as the New Red Sandstone and the Continental Intercalaire tell the same story. The uniformity of these deposits across continents separated by oceans demonstrates that they were once part of a single continuous environment, the arid interior of Pangea. Cross-bedded layers preserve the shape of dunes, while ripple marks and desiccation cracks capture the ephemeral presence of water. Within some formations, petrified wood and fossilized pollen provide clues to the sparse vegetation that clung to life in these dry basins. The deserts of Pangea were not static. They expanded and contracted over time as the planet's orbit and axial tilt varied. Periods of stronger monsoons brought temporary moisture, allowing ephemeral lakes to form only to vanish again as the climate returned to dryness. These cycles of flooding and evaporation left behind layered deposits called playa sediments, which display alternating light and dark bands corresponding to wet and dry seasons. Such cyclicity reflects the long-term rhythm of Earth's orbital changes known as Milankovitch cycles, which modulated climate even in the age of the supercontinent. The interior deserts also bore witness to powerful wind systems. Constant atmospheric circulation created prevailing winds that shaped dune orientation and transported sand across entire regions. Some dune fields migrated hundreds of kilometers over their lifespans. In certain areas, the wind-deposited loess fine silt carried far from its source, forming blankets of dust that smoothed the landscape. These deposits, later compacted into rock, reveal how the energy of moving air left its imprint on solid Earth. Though barren, the deserts played a vital part in Earth's geochemical balance. Weathering in dry conditions released mineral dust that interacted with the atmosphere, influencing the concentration of greenhouse gases. Iron and calcium carried by dust reacted with carbon dioxide, removing small amounts from the air over geological timescales. The deserts thus acted as a subtle but persistent regulator of climate. Their vast surfaces reflected sunlight, contributing to cooling, while their dust altered cloud formation and rainfall distribution. Over millions of years, these feedbacks helped stabilize planetary temperature, even as tectonic and volcanic forces drove larger shifts. At night, when the heat of the day escaped into the thin, dry air, the temperature plummeted. The stars would have been brilliant above the dark expanse unblurred by moisture or haze. Winds moved sand in slow cascades down the slopes of dunes, a quiet motion that never ceased. The desert of Pangea was both the most lifeless and the most enduring feature of the supercontinent, a realm where geological and atmospheric processes met in their purest form. It stood as the silent counterbalance to the stormy coasts and fertile river plains elsewhere, a region that captured the extremes of a world made by the union of continents. Even now, long after the breakup of Pangea, the memory of those deserts remains preserved in red rock scattered across the modern continents, reminders of a time when the center of the Earth's land was a vast sunlit emptiness under the steady arc of a Permian sky. Beneath the silent surface of Pangea, forces of extraordinary magnitude continued their slow, invisible work. The mountains that mark the seams of the supercontinent were not permanent. Deep below, the same thermal currents that had driven the continents together were already beginning to pull them apart. The mantle, a region of hot, slowly moving rock extending nearly 3,000 kilometers deep, circulated like a sluggish ocean of stone. Heat rising from Earth's core set this mantle into motion, forming vast convection cells. Where material ascended, it thinned and stretched the overlying crust. Where it sank, it dragged oceanic plates downward into subduction zones. This unending flow generated the tectonic energy that assembled Pangea, and in time it would also become the force that would undo it. The interior of the supercontinent thickened by collisions trapped heat beneath its crust. Over millions of years, this heat accumulated, softening the lower lithosphere and creating zones of weakness that would later serve as pathways for rising magma. The crust bulged in places and fractures began to form, marking the earliest hints of rifting. These fractures, though small at first, were the first signs of instability in an otherwise solid world. Mantle plumes, columns of hot, buoyant rock rising from deep within the mantle, pushed against the base of the crust, thinning it from below and generating volcanic activity along the surface. Each plume carried energy from Earth's interior toward the surface, releasing it as lava gases and heat. The slow breathing of the planet thus continued beneath the apparent stillness of the continents. In regions where the crust was stretched, such as the future margins of the Atlantic linear valleys, formed bordered by fault scarps. These proto-rifts, often filled with lakes and sediments, record the earlier stages of the separation process. But during most of Pangea's existence, the deep forces remained balanced, and the supercontinent endured. The subduction zones ringing Panthalassa continued to recycle oceanic crust-feeding volcanoes and earthquakes along its margins. These regions were zones of intense activity, the outer boundary of a continent otherwise stable within. Volcanic arcs flared above descending slabs of seafloor, while tremors rippled across the crust as it adjusted to new stresses. The cycle of creation and destruction persisted, a planetary mechanism that neither rested nor reversed. The gravitational weight of Pangea's thick crust also influenced the mantle below. As mountains rose and eroded, their mass shifted, producing subtle changes in pressure that propagated downward. Over time, these variations affected the pattern of convection, altering the locations of upwelling and downwelling zones. The deep Earth responded to the movement of its surface just as the surface responded to the deep. This interplay between crust and mantle formed the foundation of what geologists now call the supercontinent cycle, a self-regulating system in which continents assemble, persist for a time, and then fragment again. Pangea represents one chapter in this ongoing story, its rise and eventual breakup, both consequences of the same geodynamic processes. Inside the crust, fluids and molten rock circulated through fractures, depositing minerals and generating hydrothermal systems. These environments concentrated metals such as copper, lead, and zinc, creating veins that would one day become sources of ore. The heat of the interior also fueled metamorphism, transforming existing rocks into new forms under pressure. In some regions, ancient sediments metamorphosed into schist and gneiss. In others, magma intruded as granite cooling slowly within the deep roots of mountains. These transformations, invisible from the surface, record the immense forces shaping the planet from within. Even as the surface appeared static, the mantle's motion never ceased. The interior of the Earth is a place of constant flux. Beneath Pangea, heat from the core was transferred upward by the slow rising of mantle material. As it reached the base of the lithosphere, it spread laterally, transferring energy outward. This motion produced broad regions of uplift, sometimes elevating entire continental interiors by several hundred meters. The crust, though rigid on human scales, behaved like a flexible shell under such pressures. It bent and warped, forming gentle domes and basins that redirected rivers and altered drainage systems. Some of these uplifts became the future sites of rift valleys. Others sank into subsidence, collecting sediments that would later preserve the fossils and minerals of the age. Mantle convection also generated magnetic fields through the motion of molten iron in the core. As rocks formed on the surface, they captured the direction of this magnetic field, preserving a record of its changing orientation. By studying these paleomagnetic signatures, scientists have reconstructed the movement of continents over time, confirming how Pangea rotated slowly across latitudes during its existence. The alignment of these magnetic minerals provides one of the most detailed maps of Earth's internal dynamism, a record written not in ink but in the orientation of atoms frozen within stone. Volcanic activity at the margins of Pangea continued to release gases into the atmosphere, linking internal and external systems. Carbon dioxide emitted from volcanoes influenced global temperatures, while sulfur dioxide from eruptions affected atmospheric chemistry and sunlight reflection. These interactions show how deeply the planet's surface and interior are intertwined. The balance between volcanic outgassing and weathering on land helped regulate Earth's long-term climate, maintaining temperatures suitable for life despite vast geological upheavals. Beneath the crust at the interface between lithosphere and mantle, seismic waves now reveal patterns of density and temperature that trace back to these ancient events. Some regions of the deep mantle still carry remnants of subducted oceanic plates from the time of Pangea, preserved as cooler, denser zones known as slabs. Others hold hotter regions that once corresponded to mantle plumes. These deep structures, detected by modern geophysics, demonstrate that the memory of Pangea is still imprinted within the planet's interior. In essence, Earth's deep engine never stops rewriting its own architecture. During Pangea's time, the internal heat flux was slightly higher than today, as the planet continued to cool from its formation. This greater energy output drove more vigorous mantle convection and faster plate movement. As a result, the crust experienced higher rates of uplift volcanism and deformation. The deep roots of the supercontinent acted as insulators, trapping heat below and creating conditions that eventually destabilized it. In this sense, the mechanism that built Pangea also contained the seeds of its disintegration. Every mountain that rose added weight. Every convergence of crust stored stress that would one day demand release. The Earth's interior obeys no final equilibrium, it evolves through endless motion. Over tens of millions of years, stresses accumulated within Pangea's interior, preparing the way for the first rift zones that would later split the supercontinent apart. But during its long Middle Age, the planet's deep forces remained in balance, maintaining a fragile harmony between creation and destruction. It was a world resting upon restless foundations, where every calm plain and quiet sea concealed movement far beneath. The hidden forces below were both the architect and the undoing of the greatest landmass the Earth had ever known. They remain so today, guiding the continents in their slow, patient drift, a reminder that even the most solid ground is only a temporary expression of the ceaseless motion within the planet's heart. The first signs of Pangea's breakup began quietly. For tens of millions of years after its formation, the supercontinent appeared stable, but beneath its surface tension was mounting. The crust, thickened by collisions, had grown heavy, and heat trapped beneath it slowly weakened its foundations. Subtle uplift appeared in certain regions as mantle plumes pushed upward, creating domes that stretched the overlying rock. Faults developed along lines of weakness left from earlier collisions, and as the crust pulled apart, valleys began to sink between rising flanks. These rift zones mark the earlier steps toward division. What had once been a single continuous landmass was beginning to fracture, though the process would unfold over tens of millions of years. The breakup was not sudden but gradual, the slow reversal of the assembly that had brought the continents together. One of the first regions to show this change lay near the future site of the Atlantic Ocean. During the late Triassic, roughly 200 million years ago, the interior of Pangea began to stretch. The forces came from below as mantle convection shifted and new plumes rose toward the lithosphere. These plumes caused the crust to dome and thin, forming great rift valleys. Volcanic eruptions accompanied the stretching, filling the fractures with basalt and releasing vast amounts of gas into the atmosphere. These eruptions were part of what is now known as the Central Atlantic Magmatic Province, one of the largest volcanic events in Earth's history. It covered millions of square kilometers, with lava marking a turning point between the Triassic and Jurassic periods. The outpouring of magma weakened the crust further, and eventually the rifts deepened until they reached the mantle, allowing seawater to flood in. This was the birth of a new ocean, though at first it was only a narrow basin between diverging plates. The breakup of Pangea had begun in earnest. Other regions of the supercontinent experienced similar stretching. In what is now East Africa and Antarctica, rift systems formed where the crust was under tension. In western North America, compressional forces from subduction along Panthalassa's margin caused the land to crumple and rise even as the interior began to sag. The pattern of stress across the supercontinent was complex, driven by deep mantle flow and the gravitational pull of descending slabs at the edges. Over time, these combined forces tore Pangea into fragments that would become the continents of the modern world. The process of rifting changed the planet's climate as well. As continents drifted apart, new coastlines formed, and ocean currents reorganized. The once arid interior of Pangea gave way to smaller, more moderate climates along the emerging seas. Moisture from the oceans could now reach farther inland, breaking the long drought that had characterized the supercontinent's center. In place of vast deserts came new ecosystems, coastal plains, lagoons, and shallow marine environments that supported a surge in life during the Jurassic. The breakup of Pangea thus reshaped not only geography, but also the conditions for evolution. During the earliest stages of rifting, the planet experienced a time of instability. The volcanic activity associated with the Central Atlantic Magmatic Province released large quantities of carbon dioxide and sulfur dioxide, altering atmospheric composition. The sudden warming that followed contributed to one of Earth's mass extinction events, the Triassic-Jurassic extinction, which saw many reptile groups, amphibians, and marine species vanish. In their absence, new life forms would rise, including the dinosaurs that came to dominate the Mesozoic era. The geological transformation of Pangea had therefore direct consequences for the biosphere, linking the deep processes of the Earth's interior with the evolutionary path of life. As rifting continued, the continents moved slowly apart. North America and Africa separated first their drifting margins, leaving behind matching faulted edges, now seen along the eastern coast of North America and the western edge of Africa. To the east, the Tethys Ocean expanded, opening between Laurasia in the north and Gondwana in the south. This growing sea became a cradle of biodiversity, its warm waters teeming with marine reptiles, ammonites, and coral reefs. To the west, Panthalassa persisted, though its margins changed shape as subduction zones migrated. The pattern of oceanic and continental plates had been permanently rearranged. The geological evidence of this shift is preserved in the rocks. Thick sequences of basalt mark the sites of ancient lava flows, while layers of sediment record the filling of rift basins with debris eroded from the surrounding highlands. In some regions, fossils of freshwater organisms such as fish and plants are found within these basins, showing that lakes occupied the rifts before they connected to the sea. Over time, these lakes gave way to shallow marine conditions as seawater advanced, leaving behind sequences that document the gradual transition from land to ocean. Magnetic minerals within the basalt also record the orientation of Earth's magnetic field at the time of their formation. By analysing these magnetic stripes on the seafloor, scientists can trace how new crust formed as the continents moved apart, confirming the steady widening of the Atlantic Ocean through geological time. The forces driving this breakup were part of a global system. As the Atlantic opened, other parts of Pangea experienced similar changes. In the southern hemisphere, Gondwana began to fragment into smaller pieces that would become South America, Africa, India, Australia, and Antarctica. The splitting was accompanied by more volcanism, particularly in regions like the Karoo and Ferrar provinces. Each eruption marked a step in the planet's ongoing reorganization, releasing gases that influenced global climate and accelerating the transition toward a new geologic era. Even as the continents drifted apart, the memory of their former unity persisted in the patterns of mountain ranges, rock types, and fossils that matched across oceans. The coastlines of South America and Africa still fit together with remarkable precision, and the same geological formations can be traced across both continents. These correlations provided the evidence that first led geologists to recognize the existence of Pangea and the reality of continental drift. The breakup of the supercontinent thus not only reshaped the world, but also provided the data by which its story could later be understood. The transformation from one land to many marked the beginning of the modern Earth. Ocean circulation became more complex, climates diversified, and ecosystems flourished in new isolation. The world that followed was dynamic and evolving, its continents drifting apart like slow-moving rafts on the mantle's convective sea. The legacy of Pangea endures in the arrangement of today's continents, in the geological seams that mark their joining and parting, and in the deep ocean ridges that continue to widen, the basins begun during its dissolution. What began as subtle fractures in the crust grew into the structure of the modern world, a reminder that every landscape, no matter how enduring it seems, is only a momentary expression of the planet's perpetual motion. As the fragments of Pangea continued to drift apart, new oceans were born, and with them the foundations of the modern continents began to take shape. The slow spreading of the seafloor between separating landmasses created ridges that mark the boundaries of new tectonic plates. Magma from the mantle welled up along these ridges, solidifying as basalt and pushing the continents farther from one another in a steady, unhurried motion measured in centimeters per year. What began as narrow rifts during the late Triassic widened into full ocean basins by the Middle Jurassic, transforming the geography of the planet. The Atlantic Ocean was the most prominent of these new bodies of water, though at first it was only a slim corridor between Africa and North America. Over millions of years the gap expanded, carrying the continents to their present positions. This widening did not occur uniformly. In some regions, spreading rates were faster, creating broad ridges and wide abyssal plains. In others, movement was slower, leaving rougher, more fractured terrain. The magnetic minerals within the basaltic crust captured the direction of Earth's magnetic field at the time of their formation, forming symmetrical patterns of magnetic stripes on either side of the mid-ocean ridge. These alternating bands of normal and reversed polarity record the planet's magnetic reversals through time, a natural archive of motion preserved beneath the sea. The growth of new oceanic crust also brought changes to the atmosphere and climate. As fresh rock interacted with seawater, chemical reactions absorbed carbon dioxide, gradually moderating greenhouse conditions that had intensified during the volcanic events of the Triassic-Jurassic boundary. The expansion of shallow continental shelves along the new coastlines created habitats for marine life, while ocean currents began to circulate through the narrow basins, redistributing heat and nutrients. The world that had been dominated by a single ocean and a single continent now entered a period of dynamic balance between land and sea. The Tethys Ocean, once a narrow seaway, expanded between Laurasia and Gondwana, forming a warm tropical belt that connected the eastern and western hemispheres. This ocean became one of the most biologically productive regions on Earth. Coral reefs flourished along its margins, ammonites and marine reptiles filled its waters and sediments, rich in organic material accumulated on its floor. Many of today's mountain ranges in southern Europe, the Middle East and Asia originated from the later closure of the Tethys as continents converged once more. In this way, even as new oceans opened, others began their slow demise, showing that the surface of the Earth is never static, but constantly rearranging itself through cycles of creation and destruction. As the Atlantic widened, Africa, South America and North America acquired long, passive margins where tectonic activity was minimal. These new coastlines developed wide continental shelves that supported diverse ecosystems. Sediments washed from the continents accumulated in thick wedges, forming deltas and shallow marine deposits. Over time, these sediments hardened into sandstone and shale, recording the gradual encroachment of the sea. In contrast, the western edges of the Americas became active margins where subduction zones consumed oceanic crust and produced chains of volcanoes. The difference between passive and active margins became one of the defining features of Earth's later history. The birth of new oceans altered weather patterns on a planetary scale. As coastlines multiplied, moisture from the sea could penetrate farther inland, softening the arid conditions that had characterized Pangea's interior. Rainfall increased, vegetation spread, and climates diversified. The global temperature stabilized as the distribution of heat between land and ocean became more even. Fossil records show a resurgence of plant life during the Jurassic, with ferns, cycads and conifers covering much of the land, while in the oceans plankton populations expanded, forming the base of new food webs. The biosphere was responding to the geological reorganization of the planet, thriving in the newly varied environments. Yet the process of continental breakup also carried environmental costs. The volcanic activity associated with seafloor spreading and the formation of new crust released carbon dioxide and other gases into the atmosphere. At times, these emissions contributed to warming events and fluctuations in sea level. The interplay between tectonics and climate continued to shape the evolution of life-driving adaptation and extinction alike. The rise of dinosaurs and the diversification of marine reptiles occurred within this changing world, their success partly dependent on the ecosystems formed along the coasts of the new oceans. Sedimentary evidence from the margins of the Atlantic and Tethys reveals alternating layers of marine and terrestrial material, showing how shorelines advanced and retreated as sea levels changed. These transgressions and regressions were controlled by the rate of seafloor, spreading the accumulation of sediments and the volume of water locked in polar ice. Each fluctuation left a record in stone, a sequence of fossils and minerals that traces the oscillation of ocean and land over tens of millions of years. The birth of new oceans was therefore both a geological and a biological event, expanding the range of life and creating new pathways for evolution. The deep ocean basins that emerged during this time also began to act as carbon sinks. Organic matter falling from the surface waters accumulated in the sediments, sequestering carbon and influencing long-term atmospheric composition. The interaction between ocean chemistry and tectonic activity established the modern carbon cycle, in which geological processes and biological systems are intertwined. This connection ensured the planet's stability through feedback loops that balanced volcanic emissions with sedimentary burial. As the continents drifted farther apart, their outlines began to resemble those of the modern world. North America moved northwestward, carrying fragments of volcanic arcs and oceanic crust that would form the basis of future mountain ranges. South America rotated slowly, separating from Africa, but retaining geological features that still mirror those on the opposite shore. India began its long journey northward toward Asia, while Antarctica and Australia started to drift toward the poles. Each movement was imperceptible in any human time frame, yet relentless over millions of years. The pattern of magnetic anomalies on the ocean floor reveals these motions in exquisite detail, a frozen map of the planet's restless skin. The breakup of Pangea thus gave rise to a planet of islands and continents, each surrounded by new oceans that reshaped climate currents and life. The legacy of this transformation endures in every modern coastline, in the spreading ridges that bisect the ocean basins, and in the deep trenches where the seafloor descends back into the mantle. The Earth that emerged from Pangea's disintegration was one of diversity of geography, of climate, and of life itself. It was the beginning of the world as it exists today, born from the slow separation of a once unified land beneath a single sky. Even as the continents drifted into their new positions, the Earth retained the scars and memories of Pangea. Across modern landscapes, the evidence of that ancient union remains visible in mountain ranges that once formed its spine, in coastlines that still fit like puzzle pieces, and in fossils that match across oceans now thousands of kilometers apart. These traces are the enduring testimony of a time when all land was one. The study of these connections allows geologists to reconstruct the geography of the ancient world, piecing together the sequence of events that built and broke the supercontinent. Among the most striking correspondences are those between South America and Africa. The coastlines of the two continents mirror each other with remarkable precision, a clue first noticed long before the theory of plate tectonics was accepted. Along the eastern coast of South America and the western margin of Africa, identical rock formations can be found, their strata and fossils perfectly aligned. Layers of sandstone and shale deposited in the same environments lie today on opposite sides of the Atlantic, while ancient volcanic rocks of the same age mark where the continents were once welded together. In both regions, the remains of the same freshwater reptile Mesosaurus occur in Permian sediments. This animal could not have crossed an ocean, yet its fossils appear on continents now separated by an ocean thousands of kilometers wide, proving that those lands were once united. Farther south, similar evidence links India, Antarctica, Australia, and Africa. Each of these continents contains deposits of a distinctive plant fossil known as Glossopteris, a seed fern that once spread across the southern part of Pangea known as Gondwana. The distribution of this fossil, along with matching glacial deposits found in each of these regions, shows that they shared a common environment during the late Paleozoic. Grooves carved by moving ice still mark the rocks, all pointing in directions consistent with a single massive ice sheet that covered much of Gondwana when it lay near the South Pole. When plotted on maps reconstructed from paleomagnetic data, these glacial paths converge, providing clear proof that the southern continents were joined. The same pattern of alignment extends to the northern hemisphere. The Appalachian Mountains of North America share their origins with the Caledonian Ranges of Scotland and Scandinavia, as well as with the Variscan belts of Western Europe and North Africa. Their rocks and structural trends match across what is now the Atlantic, revealing that they were once part of a continuous mountain system running along the core of Pangea. The evidence extends beyond visible geology into the magnetism of rocks. When volcanic or sedimentary rocks form, tiny minerals within them align with Earth's magnetic field. Over millions of years, as continents drift, these magnetic directions shift. By studying the magnetic orientation in rocks from different continents, scientists can determine how those continents move through time. When these data are plotted, the paths of apparent polar wander for different continents converge during the period of Pangea, indicating that they were joined in a single body before diverging again as they separated. This magnetic signature is one of the most precise tools for reconstructing continental motion, providing a quantitative confirmation of what fossils and rock strata already suggest. The record of Pangea is also preserved in the sediments of its interior basins, across regions such as the Amazon basin, the Sahara, and the interior of North America. Layers of red sandstone and shale document the arid environments of the supercontinent's center. The mineral composition and grain size of these rocks match across continents, indicating that they were formed in similar conditions within one vast desert system. In some areas, these deposits contain the same species of fossilized plants and animals, further linking their origin. The global distribution of these features demonstrates that the geological memory of Pangea is not confined to any single region, but woven into the structure of the entire planet. Modern technology allows these ancient patterns to be visualized in detail. Satellite measurements of gravity and magnetism reveal subtle variations in the crust that correspond to ancient sutures, the zones where continents once collided and fused. These hidden boundaries run beneath mountain ranges and across continental interiors, marking the sites of long-vanished oceans that closed during Pangea's formation. In some cases, the composition of rocks within these sutures preserves the exact moment of collision, containing high-pressure minerals that formed deep within subduction zones. These mineral assemblages act as time capsules, recording the temperature and pressure conditions of the early Earth. Through them, scientists can trace not only the position of continents, but also the mechanics of their assembly and breakup. The story of Pangea is further confirmed by the distribution of mineral resources. Ore deposits such as gold, tin, and copper occur in patterns that make sense only when the continents are reassembled into their ancient configuration. Likewise, coal seams of similar age appear in North America, Europe, and Asia, indicating that they were once part of continuous swampy lowlands before being divided by oceans. Even oil and gas reserves in the Middle East, North Africa, and the Gulf of Mexico trace their origins to sediments laid down along the same continental margins when Pangea began to rift apart. The fingerprints of this ancient geography remain deeply embedded in the structure of modern economies as much as in the crust of the planet. The continuity of biological evidence adds another layer to the reconstruction. Fossil lineages show how species once ranged across continents, now separated by oceans. The similarities among early reptiles, amphibians, and plants across these regions point to common ancestry during the time of the supercontinent. As the continents drifted apart, these populations became isolated, leading to evolutionary divergence. The patterns of biogeography that define modern ecosystems, unique species in Australia, related forms in Africa and South America, can all be traced back to separations that began with the fragmentation of Pangea. Thus, the planet's living distribution is itself a map of its tectonic past. Even the ocean floor carries the imprint of Pangea's story. The pattern of mid-ocean ridges, fracture zones, and magnetic anomalies corresponds to the sequence of spreading that began with the breakup of the supercontinent. Where the Atlantic now lies, magnetic stripes mirror each other across the ridge, showing how the seafloor has expanded symmetrically over time. The oldest oceanic crust dates back only about 200 million years, the same age as the final stages of Pangea's division. This coincidence confirms that the supercontinent's breakup and the creation of new oceans were parts of the same process, the continuous renewal of Earth's surface driven by internal heat. In every mountain chain, in every basin of sediment, in every alignment of fossils and minerals, the mark of Pangea persists. Though the continents have long since drifted apart, their shapes and structures still echo their shared origin. The Earth today is a mosaic assembled from the remnants of that ancient unity. Each rock layer and fossil bed carries a fragment of the story, and together they form a record of connection that endures across both space and time. The traces of Pangea are not just buried in the past, they are built into the ground beneath every continent, reminders that all land was once joined in a single restless whole. The evidence of Pangea extends even deeper than the surface rocks and matching coastlines. It is written within the microscopic structures of minerals and the geochemical compositions that formed during its rise and fall. Every grain of sand, every crystal of zircon, and every layer of sedimentary rock contains isotopic signatures that serve as timestamps of the processes that shape the supercontinent. These traces allow scientists to follow the sequence of events not only through visible fossils or mountain belts, but through the atomic memory preserved in the crust itself. In laboratories, thin slices of ancient rocks are analyzed to reveal their isotopic ratios, proportions of elements such as uranium, lead strontium, and neodymium. These elements act as natural clocks decaying at predictable rates that allow the ages of rocks to be measured with remarkable precision. The ages of metamorphic minerals within the mountain belts of Pangea cluster around the time of its assembly, roughly 300 million years ago, confirming that immense heat and pressure altered them during continental collision. Likewise, igneous intrusions formed during this time contain isotopic evidence of magma generation deep within the crust, proving that mantle-derived material rose upward during the suturing of the land masses. Each isotopic system tells part of the story, and when combined they reconstruct a chronological record of the supercontinent's life cycle, from the closing of oceans to the final stages of breakup. Geochemical signatures also record the environmental conditions that prevailed during Pangea's existence. The ratios of carbon and oxygen isotopes in marine limestones reveal shifts in temperature, salinity, and atmospheric composition. During the late Carboniferous, carbon isotopes indicate high levels of organic burial as vast swamp forests captured carbon dioxide from the air. Later during the Permian, a reversal appears in the record carbon isotope values decrease, signaling widespread oxidation and the release of carbon back into the atmosphere as the climate grew drier. These data align with sedimentary evidence of retreating wetlands and expanding deserts, confirming that Pangea's interior became increasingly arid as the supercontinent matured. The oxygen isotope record shows cooling during the late Carboniferous glaciations, followed by warming as volcanic activity, and the reduction of ice altered global climate balance. The planet's chemistry shifted in step with its tectonics, each influencing the other, in a tightly coupled feedback system that spanned millions of years. Fossil pollen and spores preserved in sediments add microscopic testimony to these transitions. The pollen grains of seed ferns and early conifers reveal how vegetation changed as climates shifted. Their distribution across modern continents demonstrates the continuity of plant life across what were once unified ecosystems. Even microscopic remains of plankton in marine sediments record the response of oceanic life to changing currents and temperatures. These fossils, though invisible to the naked eye, carry within them the fingerprints of global transformation. In addition to biological and chemical evidence, the magnetic record embedded in rocks provides a continuous narrative of continental drift. Tiny magnetic minerals align with Earth's magnetic field as they form locking in the direction of the poles. By measuring these orientations in rocks of different ages, scientists can determine how continents rotated and moved through time. The alignment of magnetic poles in rocks from different continents forms continuous paths, when the continents are reassembled into Pangea, but diverging paths when they are placed in their current positions. This convergence confirms that all the continents once shared a single orientation before drifting apart. The paleomagnetic record also shows how the supercontinent rotated slowly during its existence, gradually shifting northward as the Permian and Triassic periods progressed. This drift altered climatic zones and redistributed sunlight across latitudes, influencing both weather patterns and evolution. Minerals formed during Pangea's assembly retain traces of the enormous pressures they endured. Some contain inclusions of other minerals that could only have formed at great depths, indicating that sections of the crust were buried tens of kilometers below the surface during continental collision. Later, as erosion stripped away the overlying material, these deep rocks were exhumed and exposed, bringing the history of the interior to light. Zircon crystals, exceptionally durable and resistant to alteration, preserved the isotopic fingerprints of their origins. Analysis of zircon grains from mountain belts that once lay along Pangea's seams shows consistent ages and chemical compositions across continents, confirming their shared history. These grains, smaller than grains of sand, are fragments of a much larger story written at the atomic scale. In some cases, the isotopic record reveals fluctuations in atmospheric oxygen linked to the evolution of life. During the late Paleozoic, oxygen levels were high, supporting giant insects and amphibians. By the Permian, these levels fell, possibly due to changes in weathering and volcanic outgassing. Such variations are recorded in the oxidation state of iron-bearing minerals and in the ratios of sulfur isotopes found in marine rocks. Through these chemical markers, scientists reconstruct not just the physical geography of Pangea, but the very composition of its air and oceans. The combination of all these datasets, fossil, isotopic, magnetic, and structural, creates a coherent picture of a living planet in motion. The assembly of Pangea unified ecosystems, redistributed climates, and altered the balance of gases in the atmosphere. Its eventual breakup diversified environments, once again creating isolated continents that followed separate evolutionary paths. This cycle of union and division written into the rocks and minerals is part of a much larger pattern that repeats over geological time. Supercontinents have formed and dispersed several times throughout Earth's history, each cycle lasting roughly 500 million years. Before Pangea there was Rodinia, before Rodinia perhaps Nuna, and in the far future the continents may once again merge into another great landmass. The evidence suggests that Earth operates under a rhythm of gathering and scattering, a deep geological heartbeat that regulates the surface environment over billions of years. The study of Pangea's isotopic and mineral records thus reaches beyond the past. It provides insight into the processes that continue to shape the world today. The same mantle currents that once pulled the continents together still flow beneath the crust. The same magnetic field that aligned ancient minerals continues to shift and reverse. The same isotopic systems that recorded Pangea's climate are recording the present one layer by layer, grain by grain. The memory of the supercontinent persists in every rock, every ocean current, and every breath of wind shaped by mountain chains that were born in its making. Through these tiny and enduring traces, the story of Pangea remains alive within the Earth itself, a story written not in words but in elements carried forward across time by the steady processes of the planet's deep interior.